From Sojourner to Perseverance, a comprehensive analysis of 7 Mars rovers and their discoveries. Introduction. The exploration of Mars has been a cornerstone of planetary science, with rovers playing a pivotal role in unraveling the mysteries of the red planet. From the first successful rover Sojourner to the modern marvel Perseverance, each mission has significantly contributed to our understanding of Martian geology, climate, and potential habitability. This report provides a detailed overview of 7 notable Mars rovers, their missions, discoveries, and the advancements they represent in space exploration technology. 1. Sojourner rover. Launch and landing. Launch date, December 4, 1996. Landing date, July 4, 1997. Sojourner was the first successful Mars rover, part of NASA's Mars Pathfinder mission. Its primary mission was to demonstrate the feasibility of a mobile robotic spacecraft for exploration. Key discoveries. Sojourner analyzed a variety of rocks and soil, providing the first chemical analyses of Martian materials. It identified and characterized the rock yogi and others, revealing evidence of the planet's past conditions. Mission duration. Originally planned for 7 days, Sojourner operated for 83 days, significantly exceeding expectations. 2. Spirit rover. Launch and landing. Launch date, June 10, 2003. Landing date, January 3, 2004. Spirit was part of NASA's Mars Exploration Rover mission, designed to search for evidence of past water on Mars. Key discoveries. Comanche site found rocks rich in magnesium and iron carbonates, indicating a past environment that was warmer and wetter. Home plate discovered high purity silica, suggesting the presence of hot spring environments potentially favorable for microbial life. Mission duration. Spirit operated for nearly 7 years, far surpassing its expected 90-day mission. 3. Opportunity rover. Launch and landing. Launch date, July 7, 2003. Landing date, January 24, 2004. Opportunity, a twin to Spirit, was tasked with exploring the Martian surface for signs of past water. Key discoveries. Hematite blueberries found spherical mineral formations indicating past water activity. Endeavour crater discovered clay minerals that suggest a history of neutral pH water more hospitable to life. Mission duration. Opportunity lasted until June 10, 2018, completing an impressive 14.5 years on Mars and covering over 28 miles. 4. Curiosity rover. Launch and landing. Launch date, November 26, 2011. Landing date, August 6, 2012. Curiosity aims to assess the habitability of Mars and gather data on its geology and climate. Key discoveries. Found evidence of ancient riverbeds and organic molecules in the Gale crater, indicating that Mars had conditions suitable for life in the past. Mission duration. Curiosity continues to operate, providing ongoing insights into Mars' geological and climatic history. 5. Perseverance rover. Launch and landing. Launch date, July 30, 2020. Landing date, February 18, 2021. Perseverance is tasked with searching for signs of ancient life and collecting samples for future return missions. Key discoveries. Identified diverse rock types and collected samples that may contain biosignatures of past life. Conducted experiments with the MOXIE instrument to produce oxygen from the Martian atmosphere. Mission objectives. To explore the Zhurong crater, analyze surface materials, and prepare for future human exploration. 6. Zhurong rover, China. Launch and landing. Launch date, July 23, 2020. Landing date, May 14, 2021. Zhurong is China's first Mars rover, part of the Tianwen-1 mission aiming to study the Martian environment and geology. Key discoveries: analyze soil and rocks, detecting signs of water and studying the composition of Martian surface materials. Mission duration: as of late 2021, Zhurong has operated successfully, contributing valuable data on Mars. 7. Mars 2020 rover future missions. Future prospects: building upon the successes of previous missions. The Mars 2020 rover aims to enhance our understanding of Mars' potential for hosting life. Comparative analysis of rovers. The evolution of Mars rovers illustrates advancements in engineering technology and scientific inquiry. Each rover has built upon the findings of its predecessors, allowing for increasingly sophisticated exploration strategies. Technological advancements. Instruments: each rover is equipped with advanced scientific instruments such as spectrometers and cameras, which have evolved from Sojourner's basic tools to the sophisticated suite used by Perseverance. Autonomy: with each mission, rovers have gained greater autonomy, allowing them to navigate and operate independently in the harsh Martian environment. Impact on Mars exploration. The discoveries made by these rovers have profoundly shaped our understanding of Mars. Evidence of past water has crucial implications for the planet's potential to support life. The data collected continues to inform future missions and strategies for human exploration of Mars. Conclusion: from Sojourner's humble beginnings to Perseverance's cutting-edge astrobiological investigations, the journey of Mars rovers reflects humanity's relentless pursuit of knowledge. Each rover has contributed uniquely to the tapestry of Martian exploration, paving the way for future missions. The findings not only enhance our understanding of Mars but also provide insights into the broader questions of life beyond Earth. As we continue to explore, the hope remains that one day we may answer the question, did life ever exist on Mars? The exploration of Mars through the deployment of rovers has substantially altered our understanding of the planet's history and potential for life. The missions of 7 significant rovers, notably Sojourner, Spirit, Opportunity, Curiosity, and Perseverance, illustrate the evolution of technology and objectives in extraterrestrial exploration. Each rover has contributed unique discoveries that have sometimes contradicted preconceived notions about Mars' habitability, environmental conditions, and geological history. Counterintuitive discoveries. 1. Water and acidic conditions. While the discovery of hematite blueberries by Opportunity suggested that liquid water existed on Mars, it was later revealed that these environments were often acidic. This finding challenges the assumption that the presence of water always implies conditions suitable for life. The acidic waters that once soaked the Martian surface make it difficult for life as we know it to survive, indicating that while water is essential for life, its chemical properties dramatically influence habitability. 2. Non-acidic water-rich environments. Spirit's discovery of mineral-rich rocks at Comanche indicated the existence of non-acidic water, which is considered more conducive to life. This finding counters the narrative that all ancient water on Mars was hostile. The existence of this neutral pH environment suggests that there may have been regions on Mars that could have supported life, challenging the earlier belief that Martian conditions were uniformly harsh. 3. Longer lifespan than expected. Both Spirit and Opportunity were designed for missions lasting only 90 days, yet they operated for 6 and nearly 15 years respectively. This counterintuitive result underscores the resilience of these rovers and the potential for extended exploration missions, which was not anticipated when planning the missions. 4. Diverse geological history. The findings from Opportunity and Spirit revealed a complex geological history involving volcanic activity, sedimentary processes, and impacts from meteorites. The idea that Mars once had a diverse environment with various geological processes is counterintuitive to the earlier perception of Mars as a static, barren desert. 5. Organic molecules and habitability. Curiosity's identification of organic molecules in Martian soil raised the possibility of past life. However, these findings also highlight that organic molecules can form through abiotic processes, complicating the interpretation of habitability. Thus, while the presence of organic materials is suggestive, it does not confirm life, contradicting the assumption that organic molecules are always indicative of biological activity. 6. Perseverance's sample collection goals. Perseverance's mission to collect samples for potential return to Earth might imply a straightforward path to discovering life. However, the complexity of analyzing these samples and the uncertainty of what they might reveal challenge the assumption that sample return will definitively answer questions about Mars' past life. 7. Dust and solar power. Opportunity continually monitored dust on its solar panels, which affected its energy collection. The findings about dust accumulation and its impact on solar efficiency provide insights into operational challenges that were not fully appreciated before the rover's missions. These environmental factors play a significant role in the longevity and functionality of rovers, indicating that understanding the Martian environment is crucial for future missions. 8. Habitability zones. The identification of clay minerals at Endeavour Crater by Opportunity indicates that this region once had neutral pH water, making it one of the more favorable environments for life. This challenges the earlier assumption that life could only exist in specific well-defined habitable zones, suggesting that habitability could have been more widespread on Mars. These counterintuitive discoveries highlight the complexity of Mars' history and the challenges of interpreting data from extraterrestrial environments. The ongoing exploration of Mars through rovers not only enhances our understanding of the planet but also reshapes our expectations about where and how life might exist beyond Earth. Each rover's mission has contributed to a more nuanced view of Mars, emphasizing that our assumptions about other worlds must be continuously tested against the evidence collected through exploration. The comprehensive analysis of Mars rovers from Sojourner to Perseverance provides a detailed overview of the evolution of Martian exploration, but several critical aspects of these missions are often overlooked by the general public. Here we highlight these significant points, explaining their relevance to our understanding of Mars planetary science and the search for extraterrestrial life. 1. The importance of long-term data collection. While many people focus on the immediate discoveries of each rover, such as the detection of water or organic molecules, the long-term data collection aspect is frequently underappreciated. For instance, Opportunity operated for nearly 15 years, continuously monitoring Martian environmental conditions, including atmospheric dust and weather patterns. This long-term data is crucial because it provides context for understanding the planet's climatic changes over time, which is essential for developing models of past habitability. Significance: long-term studies help scientists discern trends in Martian climate and weather, allowing for better predictions of future conditions. Understanding these patterns is vital for planning future missions and potential human exploration. 2. The role of geological context in discoveries. The geological context in which rovers conducted their investigations is often simplified or overlooked. For example, Opportunity's findings of hematite, blueberries, and gypsum veins were significant not just as individual discoveries but because they were related to specific geological formations and processes. The locations chosen for rover landings were strategically selected to maximize the potential for uncovering evidence of past water and life. Significance: recognizing the geological context allows scientists to interpret findings within the broader history of Mars. It facilitates a better understanding of how geological processes have shaped the planet and influenced its habitability. 3. Technological innovations and their impact on mission success. The advanced technology implemented in the rovers, such as the rock abrasion tool RAT and the miniature thermal emission spectrometer mini-TES, is often underappreciated. These instruments not only enabled the rovers to conduct detailed analysis but also contributed to the overall success of the missions. The RAT allowed scientists to access fresh rock surfaces for analysis, while the mini-TES provided critical data on mineral compositions from a distance. Significance: the technological advancements developed for these missions have implications beyond Mars. Many of these innovations have been adapted for use in other fields including earth sciences, health and materials engineering. 4. The interconnectedness of rover missions. Each rover's mission builds upon the knowledge gathered by its predecessors. For instance, the findings of Spirit and Opportunity directly informed the scientific objectives of Curiosity and Perseverance. The transition from the earlier rovers to the later missions exemplifies a cumulative approach to planetary exploration where each mission's discoveries shape the questions and technologies of the next. Significance: this interconnectedness underscores the importance of scientific collaboration and knowledge sharing in advancing our understanding of Mars. It highlights the iterative nature of scientific inquiry, where each new piece of information can lead to more profound questions and discoveries. 5. The search for life beyond simple metrics. Public discussions often focus on whether or not life has been found on Mars, which can oversimplify the complexities of astrobiology. Each rover has contributed to the understanding of conditions that could support life rather than directly proving or disproving the existence of life. For example, Curiosity's discovery of organic molecules and diverse geological features indicates that Mars once had conditions suitable for life even if no direct evidence of life has been found. Significance: this nuanced perspective is crucial for astrobiology. It shifts the focus from a binary outcome, life or no life, to a more complex understanding of what conditions can support life. Informing future exploration strategies. 6. The role of public engagement and education. The missions of Mars rovers have played a significant role in public engagement with space science. Events such as landing days generate excitement and media coverage, but the ongoing educational efforts, such as interactive websites, virtual tours, and citizen science initiatives, are often overlooked. These efforts help demystify space science and foster interest in STEM fields among younger audiences. Significance: public engagement is vital for the continued support and funding of space exploration. It helps cultivate a new generation of scientists and engineers who will carry forward the exploration of Mars and beyond. 7. The ethical implications of planetary exploration. Another often ignored aspect is the ethical considerations surrounding planetary exploration. As we explore Mars and gather evidence of its past, the question arises about the implications for potential life forms, even if they are microbial. The planetary protection protocols aim to prevent contamination of Mars with Earth microbes and vice versa, but public discourse on these protocols is minimal. Significance: addressing ethical considerations in planetary exploration fosters responsible science. As humanity ventures deeper into space, understanding the implications of our actions becomes vital for preserving other worlds and ensuring our exploration efforts do not cause irreversible harm. Conclusion: the Mars rover missions from Sojourner to Perseverance represent a significant leap in our understanding of the red planet and its potential to harbor life. While the surface narratives around these missions often focus on singular discoveries, the broader implications, such as long-term data collection, geological context, technological innovations, interconnectedness of missions, the nuanced search for life, public engagement, and ethical considerations are equally important. Recognizing these factors not only enriches our understanding of Mars but also informs the future of space exploration and our place in the universe. 1. Significance of water discovery. The rover's Spirit and Opportunity were pivotal in revealing Mars' wet history, essential for understanding the planet's potential for past life. Spirit's findings of non-acidic water-rich environments at Comanche and Opportunity's discovery of hematite, blueberries, and gypsum veins contributed significantly to this narrative. These discoveries not only highlighted the prevalence of water on Mars but also suggested conditions that could have supported microbial life, making them critical in the quest for understanding Martian habitability. 2. Technological advancements in rover design and instruments. The Mars rovers employed state-of-the-art technology to conduct their scientific missions. Each rover was equipped with advanced instruments such as the PanCam for imaging, thermal emission spectrometers for mineral analysis, and rock abrasion tools for sample collection. The evolution of technology from Sojourner to Perseverance reflects an increasing sophistication in rover design and capabilities, allowing for more complex analyses and a deeper understanding of Martian geology and environment. 3. Long-term environmental monitoring. The long operational durations of Opportunity and Spirit provided invaluable long-term data on the Martian environment. Opportunity operated for over 14 years collecting data on atmospheric conditions, dust, and seasonal changes, which are crucial for informing future missions and understanding Mars' climate dynamics. This long-term monitoring showcases the importance of sustained scientific observation for planetary exploration. 4. Impact on future Mars missions. The findings and technological developments from the Spirit, Opportunity, Curiosity, and Perseverance missions have significantly influenced the design and objectives of subsequent Mars explorations. The knowledge gained from previous rovers has informed the scientific questions that newer missions seek to address, particularly in astrobiology and geology. This legacy of learning underscores the collaborative nature of scientific inquiry and the importance of iterative progress in space exploration. These points serve as a foundation for in-depth analysis and discussion about the evolution of Mars exploration, the significance of water in the search for extraterrestrial life, the role of technology in advancing scientific understanding, and how past missions shape future endeavors in planetary science. 1. The Apollo Program 1961–1972. The Apollo program was a series of space missions conducted by NASA with the primary goal of landing humans on the Moon and bringing them safely back to Earth. The most famous mission, Apollo 11, successfully landed astronauts Neil Armstrong and Buzz Aldrin on the Moon on July 20, 1969, marking the first time humans set foot on another celestial body. The program included several missions that contributed to scientific knowledge, including the collection of lunar samples, deployment of scientific instruments, and extensive geological surveys. Apollo missions provided crucial insights into the Moon's composition, geological history, and potential for future exploration. 2. The Voyagers 1977–present. The Voyager program, consisting of Voyager 1 and Voyager 2, was launched to explore the outer planets of the solar system. Voyager 2 made history by being the only spacecraft to visit Uranus and Neptune. The missions provided unprecedented data about the planets, their moons, and the heliosphere, significantly expanding our understanding of the solar system. Voyager 1, now in interstellar space, continues to send back data about cosmic rays and magnetic fields, while both spacecraft carry the golden record, a message to potential extraterrestrial life, showcasing humanity's diversity and culture. 3. The Hubble Space Telescope 1990–present. Launched in 1990, the Hubble Space Telescope has revolutionized our understanding of the universe. Its high-resolution images and spectroscopic data have provided insights into the age and expansion of the universe, the formation of stars and galaxies, and the existence of exoplanets. Hubble's observations have led to significant discoveries, including the observation of dark energy, the identification of distant galaxies, and the study of cosmic phenomena such as supernovae and black holes. Its legacy includes thousands of published scientific papers and a wealth of publicly available data that continues to inspire astronomers and researchers worldwide. The exploration of Mars through its rovers has provided profound insights into the planet's geological history and the potential for past life. As we look ahead, the future of Mars exploration appears promising and multifaceted, with advancements in technology and international collaboration paving the way for more ambitious missions. Predicted advancements in Mars rover technology. 1. Autonomous navigation. Future rovers will likely feature advanced AI capabilities, enabling them to navigate the Martian terrain more autonomously. This will reduce the need for real-time human intervention, allowing for more extensive exploration of difficult terrains and remote areas. 2. Enhanced scientific instruments. New rovers are expected to carry even more sophisticated instruments. For instance, miniaturized labs capable of conducting in situ analysis of samples will facilitate immediate scientific evaluation without the need to return samples to Earth. 3. Improved power sources. Solar power has been a staple for existing rovers, however, future missions may utilize nuclear power sources providing consistent energy regardless of Martian dust storms or seasonal changes. This will extend mission durations and operational capabilities. 4. Increased sample return missions. Following the Perseverance Rovers mission to collect samples, future missions could focus on returning these samples to Earth. This will allow for detailed analysis using advanced Earth-based laboratories, significantly enhancing our understanding of Martian geology and potential biosignatures. Potential discoveries and research directions. 1. Search for current life. As technology improves, the focus may shift to investigating areas that show signs of recent or even current microbial life. Rovers could be equipped with tools to detect biosignatures or biochemical markers indicative of life, particularly in subsurface environments. 2. Climate studies. Future missions may prioritize understanding Mars' climate history. Analyzing sediment layers and atmospheric samples will provide insights into climate changes over millions of years and how they affected the planet's habitability. 3. Water resources. Identifying and analyzing water resources will be crucial for future human missions. Rovers could be tasked with locating and assessing the quality of water ice and brine, which could support human life and fuel future exploration. 4. Geological diversity. The exploration will likely expand beyond the current landing sites to more diverse geological features. Missions may target areas like the polar ice caps, Valles Marineris, or ancient river valleys to understand the planet's geological evolution. International collaboration and future missions. 1. Global partnerships. The future of Mars exploration will likely see increased collaboration among space agencies worldwide, including NASA, ESA, CNSA China, and ISRO India. This collaboration could lead to shared technology, scientific data, and combined missions. 2. Crewed missions. The ultimate goal of Mars exploration is to send humans to the planet. Future missions may involve not only robotic rovers but also crewed spacecraft equipped with habitats for astronauts. Preparatory missions will focus on life support systems, radiation protection, and resource utilization. 3. Sustainable exploration. Emphasis will be placed on sustainable practices in Martian exploration. This includes developing habitats that utilize in situ resources such as extracting water from the Martian soil and creating fuel from local materials to support long-term human presence. Conclusion. The evolution of Mars rovers from Sojourner to Perseverance has set the stage for a future filled with possibilities. With advancements in technology, increased international cooperation, and a focus on sustainable practices, the next decades promise to unveil even more of Mars' secrets. The ultimate aim is not just to explore but to understand the red planet in a way that prepares humanity for its future on Mars. As we advance, the quest for knowledge about our neighboring planet will continue to inspire and challenge us, potentially leading to groundbreaking discoveries that could redefine our understanding of life beyond Earth.